Another physical requirement for microbial growth is osmosis. So whether a cell is in a hypotonic or hypertonic solution, that can affect whether the microorganisms can divide or not, or even survive. So remember that we talked about placing microorganism cells in a hypotonic solution. So remember that means that there's less solute outside the cell than there is inside the cell. And remember, hypo means less than. So remember that water likes to follow the solutes. So there's more solutes inside the cell than there is outside. So water would want to move into the microorganism cell. So water is just moving down its concentration gradient. So there's less water inside the cell and more water outside. Because of the difference in the solute concentration. And so with water moving into the cell, as long as the cell wall is intact, the cell wall will protect the cell from swelling up too much. But if the cell wall is damaged, or maybe it was inhibited from being synthesized, like maybe the bacteria were exposed to penicillin, then we could have the cell continue to swell and then eventually lyse. Remember, that's called osmotic lysis. So that would be important to know. And then the opposite problem would be if you place a microbial cell into a hypertonic solution. Hyper meaning more than or excessive. So you've got more solute particles outside the cell than you do inside. Remember, water likes to follow the solutes, so there's more solutes outside the cell. So water is going to follow the solutes and go out of the cell. And there's actually less water outside the cell than inside, so water is going down its concentration gradient. So water leaves the cell, and what can happen is something called plasmolysis. And this can also kill the bacterial cell. So let's take a look at this. So here on the left, we've placed a normal bacterial cell into a hypertonic solution. Water moves out of the bacterial cell, and what happens is the cell will shrink, and as it does, it pulls the plasma membrane away from the cell wall, and that will rip the plasma membrane as it pulls away from the cell wall, and then that disintegrates the plasma membrane, and then it can't control what's going in and out anymore, and then that will kill the bacterial cells. So plasmolysis will kill bacterial cells if they get into a hypertonic solution. Okay, but there are some microorganisms that are adapted to hypertonic environments. So we talked about halophiles. So remember, halo means salt and phil means to love. And so like the archaea living in the Great Salt Lake, for example, they actually can tolerate very high salt concentrations. They've figured out a way to deal with that. And then there are microorganisms that are what we call halotolerant. So they wouldn't be able to live in the Great Salt Lake, but they can tolerate some higher salt concentrations, like they can live on the salty skin. So they can tolerate the salt that's in our sweat. So like the Staph aureus in our skin, they would be halotolerant. Okay, and then we come to this idea of what's called water activity. So this would be a good word to know. And water activity, all it is it's just a measure of how much water is available for organisms to be able to use. And this depends on the number of solutes that are around. So the more solutes that are around, the more things that are dissolved in the water likes to stick to the solutes, and that makes less water available. So the higher the solute concentration, the less water is going to be available for the organisms to use. Okay, so that would mean there's lower water activity. And this is going to be very important in food preservation. So you can see here I've got a picture of some salt that's been dissolved in some water, and you can see the water molecules are attracted to the charges on the sodium and the chloride ions, and they're surrounding that, and so it's going to make that water molecules unavailable for the cells to be able to use if they're bound to those sodium and chloride ions. Okay, here's a graph just showing you the water activity on the bottom. And water activity, the highest you can get is 1, which basically means that 100% of the water molecules are available, so there wouldn't be any solutes dissolved in the water. And then going down to 0.7, which is getting near the limit of life. Things are getting pretty dry or pretty salty, or lots of sugar or something like that, and there wouldn't be much water available at all. And here's the growth rate on the y-axis here, so the number of microorganisms that can be produced as they divide. And you see that most bacteria, they need lots of water available, so they need a very high water activity. Here's our halotolerant bacteria, for example, like Staph aureus living on our skin. So they can tolerate some salt and still divide and do okay. And then here's our extreme halophiles, like living in the Great Salt Lake. So they can tolerate some pretty high salt concentrations in their environment, and that lowers the water activity that other microorganisms would not be able to survive. And this is really important in food preservations because if you salt and dry your food, or if you add lots of sugar to it, like in honey or jelly, there's so much solute there that it's going to bind up all the water, and there's not going to be any available for the microorganisms to use, and that will preserve the food. So you probably have some honey, maybe sitting in your cupboard at home. You don't have to refrigerate it, and it can sit in your cupboard for years and not have anything grow in it. Same thing with beef jerky. It's dried and salted, and nothing's really going to grow in that beef jerky for a very long time. Because there's no water available for microorganisms to use and be able to grow on that.